I'd like to start off by thanking the organizers for giving me an opportunity to speak. I'm Kai Smith, and today I'll be talking about pillowcase homology and character varieties of tangles. So pillowcase homology is a proposed knot homology theory by Hedden, Harold, and Kirk. And so today I'll go through the construction, give some theorems relating to its computation, and also give some results about to what extent it really is a knot homology theory. So the main motivation for pillowcase homology comes from its relation with another knot homology theory, namely singular instanton homology. So this is a knot homology theory defined by Kronheimer and Mrówka, which we'll denote by I natural. And it has two main features. First is that it detects the unknot. So if any knot has the same singular instanton homology as the unknot, then that knot is in fact the unknot. There's also a spectral sequence from Kovanov homology of the mirror of the knot to the singular instanton homology of a knot. And putting those two pieces of information together give sort of the most important theorem to come out of singular instanton homology, which says that Kovanov homology actually detects the unknot. And Kovanov homology is one of the main tools of modern knot theory, and detecting the unknot is a really fundamental property of a homology to have. And so this is an important theorem, and the only way it's known to be proven is through singular instanton homology. So it's definitely an important invariant, but as we're going to see, it's going to be pretty hard to actually calculate. And so that's part of the problem pillowcase homology tries to solve. So let's look at the construction. So if we start with a knot S in the 3-sphere, we're going to start by adding an earring to it, which is this meridian of the knot along with an arc connecting the knot to the meridian, which is colored in red here. I should note that in general, singular instanton homology deals with knots in other 3 manifolds, but for today, we're going to stick with S3. So after you've added the earring, we want to consider the principal SU2 bundle on S3. And then we're going to look at the connections on that bundle. So if this is new to you, a connection is just the data that's going to take a loop in the base space and tell you how to lift it to a loop in the bundle, or more generally for paths. And one of the main tools used to study connections is their holonomy. And so if you have a loop in your base space and you lift it to a loop in the bundle, you're going to start with a point and end up with a point that's on the same fiber, but it might not be the same exact point. And so the holonomy just keeps track of how far you've moved in the fiber direction for each loop that you went around. And so we're going to let A be the set of all connections on this SU2 bundle, which are singular along the knot, and have some subtle restrictions on what the holonomy can be. But we're not really interested in the space of all connections. There's a group action on this space by the gauge group. And what we're really interested in is the quotient of this space by the gauge group. So we're going to denote that B. And the reason we added the earring was because if we didn't, the space of connections would include the trivial connection, whose stabilizer under the gauge group is big. And so when we quotient out, you're left with a singular space, which is harder to deal with. So by adding in the earring, we've removed that problem and made life a little easier for us. So we're going to study our knot by instead studying this infinite dimensional space of connections mod gauge. And we're going to study that space using Floer homology, which is sort of an infinite dimensional analog of Morse theory. And what's playing the role of our Morse function will be something called the Chern-Simons functional. And just like in Morse theory, we're going to get a chain complex, and it'll be generated by critical points of the Chern-Simons. And those are flat connections whose holonomy around the meridian of the knot gives a traceless element of SU2, except the holonomy around a meridian of this red arc should get sent to -1. And flat connections are just those where the holonomy doesn't depend on the exact loop you pick, but only depends on the loop up to homotopy type. Then we want to know what the differentials of the chain complex are, and those are given by something called instantons. And all that is a path of connections which interpolate between two of these flat connections, along with satisfying some PDE known as the anti-self-dual equation. And so, as you can imagine, these are, this chain complex is pretty hard to actually compute for any knot. You have to build an infinite dimensional space and solve PDEs on it. But there's a conjecture by Attia and Fleur that any instanton homology, such as this one, has a corresponding Lagrangian Fleur homology counterpart. And so the idea behind pillowcase homology is that it's an attempt to find this Lagrange Fleur counterpart to singular instanton homology. So let's see how it's constructed. So to start off, you start with a knot in S3, just like any other knot homology. And then, just like before, we're going to add an earring. And now we're going to want to find a sphere which decomposes our knot into two tangles. So we want to find it in a way where one of the tangles is the trivial tangle along with the earring. So in this picture, that's this smaller one here. And the other tangle kind of contains all the other information of the knot, which is the outside region in this picture. And so we split up our knot into two different tangles. And we want to note that these tangles have a common boundary, which is this 4-punctured two-sphere. And now for each of these spaces, the two tangle complements and the 4-punctured two-sphere, we want to associate to it a new space called the SU2 character variety. So for any space X, is SU2 character variety is the space of homomorphisms from pi1 of X to SU2. And we're going to mod out by the relation that two representations are equivalent if they're conjugate by an element of SU2. So this whole space, the whole SU2 character variety is pretty big. We want to restrict ourselves to just the traceless SU2 character variety. And what that means is that under this homomorphism, any meridian of our tangle or of one of the punctures on the two-sphere should be sent to a traceless element of SU2. And just like before, we're going to have an exception for this arc on the earring. So the meridian of this arc should get sent to -1. And let's see what kind of spaces we get. So the most important is the 4-punctured two-sphere. When we take its traceless SU2 character variety, we get the titular pillowcase. And so that's going to be homeomorphic to a two-sphere with 4 singular points. It'll be easier to work with if we unfold it like this. Then let's look at each of the two tangles and see what its character variety is. So the trivial tangle with the earring is going to give us a circle. And for the sake of demonstration, let's say this other tangle gives us just an arc. And now, since any representation on a tangle complement restricts to its boundary, that means we get a map from each of these spaces into the pillowcase. So for example, the circle might map in like this, and then the arc might map in like this. And now, since the pillowcase is actually a symplectic manifold, and these curves are immersed Lagrangians, we can use Lagrange Fleur theory to get a homology. But it's especially simple in this case, since we're only dealing with a surface and curves on that surface. And so the generators are given by intersections of the two Lagrangians. So anywhere the blue curve meets the red curve in the pillowcase gives a generator of the chain complex. And then differentials are going to come from bigons. And so it's a shape like this, where one side is bounded by one Lagrangian and the other by the other Lagrangian. And so a bigon like this would be a differential from this generator to this generator. So you have to pick a convention on, which color kind of stays on the right, stuff like that. So in this example, there's 3 intersections. So we have 3 generators, but there's one bigon, which gives us one differential. And so when we take the homology of that chain complex, we get something with rank 1. So let's look at how these two theories compare. So on the chain group level, there's a natural equivalence between pillowcase homology and singular instanton homology. So in pillowcase homology, an intersection in the pillowcase means there's a representation on both tangles which agree on their boundary, so we can glue them to make one representation on the entire complement of the knot and earring. On the other hand, flat connections were those that were where the holonomy is determined just by the homotopy type of a loop. And so given a flat connection, by looking at the holonomy of every element of pi1, that gives you a representation. And this will go the other way. So given a representation, you can find a flat connection with the prescribed holonomy. And there's a correspondence between the two quotients we took. So modding out by gauge modding out by the gauge group in the singular instanton homology case corresponds exactly to modding out by conjugation by elements of SU2, which is what we did in the pillowcase homology. And one thing to note is that both of these theories are Z4 graded and the gradings agree. So in terms of the chain groups, they're identical, but things aren't as clear for the differentials. So we already said that an instanton is an interpolation of flat connections. And now we know that those flat connections correspond to intersections on the pillowcase. And bigons in the pillowcase will give a similar interpolation between the two generators, but this interpolation won't necessarily satisfy the right smoothness conditions to correspond to an instanton. So, they're definitely related, which is the motivation for the Atiyah-Fleur conjecture, but we can't say that the differentials exactly agree in these two theories. So far, as I've explained everything, there's some big problems. If you tried to compute either of these theories the way I've explained so far, it just wouldn't work. And so in the singular instanton homology case, the Chern-Simons function is usually not Morse. In fact, unless you're looking at the unknot, it's not going to be a Morse function. And for pillowcase homology, the character variety of a tangle is usually not a manifold. And again, that's going to be the case as long as you're not looking at the unknot. So these are big problems. We can't take Fleur homology unless our function is Morse, and we can't take our Lagrange Fleur homology unless we actually have Lagrangians. And if they're not manifolds, then they're not going to be Lagrangians. So an example of a character variety, there's some examples here. So they always have some one-dimensional component, which is this arc in all of these examples, but they might intersect another one-dimensional piece in a way that makes it not a manifold, or they might even have two-dimensional components, like in these two examples. And both of these problems are solved with something called holonomy perturbations. So the main piece of data for holonomy perturbation is some family of perturbation curves. And looking at that tangle we had before, here's three potential different perturbation curves you could have. And how does a perturbation curve help? So in the instanton case, adding the perturbation curve, we're going to make it so that instead of looking for flat connections, we're looking for what are going to be called perturbed flat connections, which will be flat away from the perturbation curve. And then near the perturbation curve, they're going to satisfy some new condition given that depends on the holonomy of that curve. So yeah, so almost flat except near this perturbation curve. And doing that will make it so that the Chern-Simons is Morse, and you can actually take the Fleur homology. The intuition for what the perturbation curve does in the pillowcase situation is a little harder to explain, but by a theorem of Herold and Kirk, we know that for any two-stranded tangle, there is some collection of perturbation curves such that you can perturb it to get a one manifold, which will give you an immersed Lagrangian in the pillowcase. So let's look at what can happen when you try to perturb a character variety. So here are our three examples of a bad character variety. And so when adding a perturbation curve, we'll smooth it out so it looks like a one manifold. So for example, this example on the left might smooth out to one of these cases. And you can see that, in either case, we get a manifold, which is good, but we might get pretty different looking character varieties after we perturb. In particular, on the left, this smoothing is connected, and on the right, this smoothing is not connected. And that's going to make a difference. So if we want to calculate the gradings from the pillowcase picture, we want all the intersections to lie on the same connected component of both character varieties. So in this left example, these three intersections, I can grade them because they all lie on the same component of the black character variety and on the same component of the red character variety. On the other hand, on this right example, these two intersections, I can't figure out their relative grading because they lie on different components of the black character variety. So, to actually compute the gradings of your chain complex, you would really like for your character variety to be connected after you perturb it. And so in general, although computing pillowcase homology is significantly easier than computing singular instanton homology by hand, it's still pretty hard. There's not a combinatorial process to go from your tangle to a character variety to your homology. And so it's a lot of work if you have a tangle and a perturbation curve to actually figure out what the character variety is. And so you want to, you would like to know ahead of time that you have the best shot of perturbing your character variety and having it be connected. And so these next theorems address that. So first of all, if we have any perturbation curve, in order to actually smooth the character variety, it must wrap around the meridians of the tangle an odd number of times. And then furthermore, if it does that, it's going to wrap around one of the strands an odd number of times. If you close up that strand, you'll get some knot K. And then the number of components you get after perturbing is bounded below by this formula here, which includes the Alexander polynomial of the knot K. So that's a pretty simple thing to compute once you just from the picture of your tangle without having to actually compute the character variety. So here are three examples of perturbation curves, and let's see how they work with these theorems. So this first example actually wraps around the tangle 4 times. So the first theorem tells us that that's actually not going to smooth out our character variety at all. It's going to leave any singularities that are already there, and so that's just not going to help. And so we don't even have to, there's no use even starting this computation. On the other hand, these next two wrap around the tangle an odd number of times, so they pass the first test. Let's see what the second theorem tells us about them. So if we close up our two tangles here in a way that gives us two components, so a link, we'll see that we get this green component, which is the knot 6-1, and this purple component, which is the unknot. So the middle perturbation curve here wraps around the purple strand twice and the green strand 3 times. And so the strand of interest here is the green one, and the knot we get when we close it up is 6-1. And so this second theorem tells us that after we perturb with this perturbation curve, if it smooths out our character variety, it's going to have at least 5 components. So we get that by plugging in the 9 here into this formula here. And if you have at least 5 components, it's very unlikely that all the intersections are going to lie on the same component, unless the other character variety completely misses 4 of them, which is very unlikely. On the other hand, this last perturbation curve wraps around the green strand twice and the purple strand once. So this theorem now tells us if we plug in 1 for the Alexander polynomial K at -1, tells us that there's at least 1 component of the character variety after we perturb. So it doesn't guarantee that there's just 1, but it at least tells us it's possible that once we perturb, we'll end up with a connected character variety, which is what we want. So these theorems make it easy to, quickly evaluate your the decomposition of your knot and the perturbation curves that you've chosen to make sure that you're likely to get an outcome which is actually useful to you. And you didn't do a bunch of work to compute a perturbed character variety just to have it either not smooth anything or give you a chain complex which isn't graded. So as we've seen, the definition of pillowcase homology, as I've given it so far, does depend on the choice of tangle decomposition and also perturbation curves. And so for sure, one thing that's true is that the character varieties that you get depend on these choices. But one would really hope that the homology you end up with doesn't depend on these choices. And for all the computations of pillowcase homology before, which were mostly on two bridge knots and torus knots. So pillowcase homology had been computed for particular decompositions and particular perturbation curves. All known computations had the same pillowcase homology as the singular instanton homology. So it seemed somewhat likely that, you know, the definition of the pillowcase homology is independent of these choices. However, some of the things I've been working on is to compute the perturbed pillowcase homology for a bigger class of knots, and that includes pretzel knots, which are knots like these. So it's the knot in black, and then in the boxes, imagine two parallel vertical strands with the prescribed number of half twists that are on the box. So I've computed the pillowcase homology for many of these pretzel knots. And one nice thing is that I can do it with multiple tangle decompositions. So in these pictures, I'm always using the same red perturbation curve in these three examples, but I'm decomposing the knot into two tangles along three different spheres. And then the asterisk here is just to remind you that there's an earring inside this part of the tangle inside the sphere. And so doing these computations, what I get is that the three pillowcase homologies are different. In fact, the ranks are even different. So this top example has rank 15, the middle example has rank 5, and the bottom example has rank 1, which is even the same as the unknot. And so these numbers here, remember that our homology is Z4 graded, so these are just the ranks in each grading. So we can see that the pillowcase homology does in fact depend on your choice of sphere to decompose the knot into tangles. And this knot in particular, we know by a result of Lobb and Zentner, has singular instanton homology of rank somewhere between 11 and 15. So this top computation could, you know, that does match a possible rank of singular instanton homology, but the other ones definitely don't. And so from here, we know that pillowcase homology is definitely dependent on decomposition, and therefore it's not isomorphic to singular instanton homology. However, that doesn't mean that pillowcase homology is not useful. First of all, you can use it to compute the instanton chain complex and gradings, which is something that's still difficult to do from the definition alone. So doing that, you can get bounds on the rank of singular instanton homology. But furthermore, it's still possible that there's a real relationship. So looking at our Lagrangians in the pillowcase, there's a lot of structure there known as the Fukaya A infinity category. Looking at the bigons is really only looking at the simplest possible data of the Fukaya category. And so what I've shown is that if you only look at the bigon data, you don't get a well-defined homology theory. However, there's reason to expect that with a more, using more data from the Fukaya category, you could define a differential, which does give a well-defined homology theory and one that's isomorphic to singular instanton homology. Yeah, so I think that's all I had to say today. Thank you so much for listening. And if anyone has any questions, feel free to reach out. Thank you so much for listening.